Hello everyone. Today we'll dive into VoteFlow, our method for enforcing local rigidity in self-supervised scene flow. What is scene flow? In the simplest terms, scene flow is the per-point, three-dimensional motion field of a dynamic scene, which tells us how each 3D point in a point cloud moves in space over time. So a scene flow estimator takes as input two adjacent frames of point clouds and outputs a per-point motion field. Scene flow estimation usually serves as a cornerstone for downstream perception tasks, such as unsupervised object discovery and dynamic object compensation. Before we dive into VoteFlow, let's revisit a common assumption in scene flow estimation: rigid motion. Put simply, if 2 points belong to the same rigid object, they should move together, translating and rotating as a single solid body. State-of-the-art methods already try to leverage this prior in two ways. First, by adding extra loss terms or regularizers that penalize inconsistent motion among neighboring points during training. Second, by applying post-processing steps at inference time to enforce piecewise rigidity. However, there's a gap. None of these models has motion rigidity truly baked in by design. As a result, they occasionally produce inconsistent flows, especially for large objects like buses. So how to encode motion rigidity directly inside the model itself? Voting. That's our core intuition behind VoteFlow. Use voting to identify shared rigid motion. For each point, we first find its neighboring points, shown as blue stars in the figure, and calculate their potential translations, represented by arrows pointing from the blue stars to the green dots. Then, we let these neighboring points vote for a single translation vector, like the red arrow shown here. Points on the same rigid object will naturally agree. In this way, the votes indicate the motion of the point. Our main contributions in this paper are threefold. First, we propose VoteFlow, which directly integrates local rigid motion as an inductive bias into the network design of a self-supervised scene flow network. Second, our core component, a lightweight, differentiable voting module that can be used in a plug-and-play manner with any mainstream model. Last but not least, VoteFlow outperforms existing methods on the Argoverse 2 dataset, generalizes effectively to the Waymo dataset in cross-domain evaluation, and maintains real-time inference at approximately 40 frames per second. Here's an overview of the VoteFlow pipeline. VoteFlow basically follows the design of mainstream feed-forward scene flow networks. First, two consecutive LiDAR sweeps are embedded into voxel-based pseudo-images by a shared pillar feature net. Then, the pseudo-images are fused by a U-net. In parallel, our lightweight voting module also takes the pseudo-images as input and outputs voting features. At the end, we concatenate the voting features with the fused U-net features, along with the original pseudo-images, and pass them into the decoder to predict the final scene flow vectors. During training, self-supervised losses, such as C-flow loss, are applied to provide supervision. Now let's delve into the voting module, which operates in voxel space for efficiency. Its steps are: 1. For each non-empty pillar at time t, find its m nearest pillar neighbors at time t. 2. For each of those m neighbors, select n random pillars at time t plus del t within a predefined radius. 3. Use pillar indices to fetch their features from the pseudo-images. 4. For each source-target pillar pair, compute the translation vector and measure feature similarity to obtain a voting score. 5. Cast each voting score into a discretized voting space bin corresponding to its translation. 6. Pass voting space into a CNN module to produce a compact voting feature for that pillar. 7. Gather voting features for all non-empty pillars. This process summarizes all votes into continuous feature vectors, which the decoder then uses to enforce motion rigidity. Here are our main quantitative results. For in-domain evaluation, where the model is trained and tested on the same dataset, VoteFlow consistently outperforms prior self-supervised baselines on both Argoverse 2 and Waymo across nearly all metrics and categories. On the right side, we show cross-domain performance, training on Argoverse 2 and testing on Waymo. Even without domain adaptation, VoteFlow generalizes much better than other self-supervised methods. Moreover, VoteFlow runs in real time with around 40 FPS on an A100 GPU. Therefore, by embedding the rigidity motion as an inductive bias, VoteFlow achieves state-of-the-art performance and superior cross-domain robustness. We further integrate our voting module into the supervised FastFlow 3D and the unsupervised CFlow, consistently improving their performance. This table highlights the plug-and-play nature of our voting module and demonstrates the benefits of embedding motion rigidity into network design. Now let's look at some visual examples. In the first row, compared to baseline method, our method predicts more consistent predictions across the entire bus, yielding uniform coloring. Nevertheless, our method still encounters difficulties in yielding completely accurate predictions for this larger object. Similarly, in the middle row, our model again achieves coherent coloring, indicating consistent motion. In the final row, VoteFlow delivers consistent predictions with fewer false positives, closely matching the ground truth. We now visualize several example voting spaces for a single anchor pillar, marked by a red triangle in the ground truth flow. In the middle column, each bin represents a discrete translation. The center cross indicates zero motion, while the grid edges correspond to the maximum allowed translation in each direction. The arrow from the center to the argmax bin is the voted translation. Notice how that arrow aligns almost perfectly with the pillar's true flow. This visualization confirms that, for rigid regions, the voting distribution is peaked around the correct motion direction, just as we intended. Here are the main takeaway messages. Motion rigidity, as an inductive bias, is crucial for scene flow estimation. Integrating motion rigidity into network design improves the performance and generalizability of the model. Current voting space resolution constrains our ability to capture long horizon motion. Future directions include designing mechanisms for long horizon rigid motion encoding and incorporating multimodal data to further improve scene flow prediction. Thank you for watching. For more information, please see our paper and code. To explore additional research, visit our group's homepage. If you have any questions, please feel free to reach out to the authors.